All right, guys, we're going to go through this presentation about structures of acids and bases based on their Lewis structure. Try to go through this as quickly and painlessly as possible. All right, if we have a binary acid, all right, H bonded to just one thing, X, all right, it comes down to two things that define the strength of the acid. All right, how easy is it to remove that proton? The easier to remove the proton, the weaker the bond between H and X. So strong acids, weak bonds. The other part is how stable is the conjugate base. All right, so the conjugate base is always going to be negative, all right, almost always negative. It loses a proton. We have this negative thing afterwards. So how well can this item, this new base, hold on to that negative charge? Those are the two things that affect how strong an acid is. So if we look at these four halide acids, all right, the bond between H and F is strong. It's 567 kilojoules per mole. So because this bond is so strong, right, it has a hard time breaking. It's a hard time breaking it apart. So H is attached to F somewhat well here. Down here with HI, this bond is very weak, all right, weak bond. Because it's so weak, it's easy for this bond to be severed and for I to donate a proton. So HI, strong acid. Same thing with HBr and HCl, right? These are your strong acids. HF is considered a weak acid. And part of the reason is because it has a high bond strength. Right? And the other part that we talked about was conjugate base stability. Now, this holds true for all things, but let's look at just the halides. As we go down the periodic table, all right, the ions get bigger. So fluorine, right, is not super big at all, right? It's very small. All right. It only has two energy shells and they're very close together. All right. Iodine, on the other hand, is much bigger. It has five energy shells. All right. Much, 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 much bigger. So because of this, when fluorine is negative and we add that extra electron, it's hard to hide an electron in a really small space. All right. This makes this unstable. All right. Meanwhile, we plop this electron here, all right? Just gets lost in the sauce, right? It's just gone. It disperses quite easily. All right. This is much more stable. All right. We define an acid, all right, as strong or weak as its ability to ionize. All right. Part of the reason why HF is weak is not only did we say that this bond was strong, right? This is a strong bond, but F minus isn't very stable. So the F wants to link back up with the H, and this reaction goes backwards, right? And now we have, right, a weak acid. All right. Meanwhile, with HI, right, this bond is super weak, right? This bond between the H and the I, it's really weak. That bond's really, really weak. And this I is really stable, right? This reaction doesn't go backwards, and that's why HI is a strong acid. All right, last time. I minus is a, or F minus is a stronger conjugate base than I minus. Again, that's why HF is a weak acid and HI is a strong acid. All right, so we have this question here. It wants to compare the halides in the correct order from lowest pKa to highest pKa. So in case you forgot, all right, just like pH, it's an inverse scale. So really we're saying we want the largest Ka, all right, and then the smallest Ka, all right? Large Ka, strong acid, smaller Ka, weak acid. So if we just go, we want them in order from strong acids to weak acids. C and D are wrong because of the order they're listed in, but let's just make sure, let's look and see if anything else about them is wrong as well. So we know they're already incorrect, but let's see, besides being listed in the wrong order, Let's also see why they're incorrect. It says HF has the strongest bond between atoms, which makes it the strongest acid. Well, this is true. That's true, but that actually makes it the weakest acid. So again, it's incorrect there. And F minus is the weakest conjugate base of the halides. Well, we actually just said that F minus is the strongest conjugate base, so that's also incorrect. If we look at A and B, HI has the strongest bond between atoms, which makes it the strongest acid, right? And again, we said that's just like C, right? It's incorrect. It has the weakest bond. So B should be correct. I minus is the weakest conjugate base. And yeah, that is correct. I minus is the weakest conjugate base. It is the largest. It has the easiest time dispersing that negative charge. All right. Oxyacids are elements that have an O and then something else, and then maybe more O's attached to them. And there's two parts to this. The ability to have extra O's means you have a greater electronegative pull. So as a conjugate base, if you're really electronegative, you're stable because you can hold that negative charge easier. And the more electronegative you are as an entire atom, the weaker that bond between H and O is, and the stronger the acid becomes. So if we look at these top four, so these are this is the perchloric, chloric, chlorous, hypochlorous acid. So perchloric acid is one of the 6 strong acids, and it's a strong acid for 2 reasons. All right, first off, all of these O's are super electronegative, and they just start pulling all of the electrons towards them. Then Cl has to pull some electrons towards it, and then this O needs to start pulling the electrons from H away, and this makes this bond really weak, and that's why this is a strong acid. The other reason why is that the OCl O minus ion is very stable. It's large, a bunch of electronegative elements, no big deal holding on to an extra electron. All right. HOCl is a very weak acid. All right. This bond here is relatively strong. There's not a lot of electronegativity pulling going on by the H or by the O to both of these things. So this bond is relatively strong, weak acid. And this isn't a very large ion, right? This is not stable. So this, if given the chance to react with an H plus, it'll grab that H plus again and reform the acid, so weak acid. All right, so we have, we want to find out what acid here is being present. So let's look at how many of these there are. There are 3 of them here, 1 of them here, and 5 of them here. All right, that makes acid 2 the weakest, and acid 3 is the strongest. Because the stronger the acid you are, the more H's you can donate. All right, so if we look here, we have HClO, HIO, and HBr. All right, so of these 3, all right, they're all different oxyacids. If we look at their conjugate bases, right, we want a conjugate base that's going to have the ability to hold on to a negative charge and be somewhat stable here. The more stable this, the stronger the acid. Well, of these 3 ions, all right, ClO minus is the most stable. It's the most electronegative. All right. IO is the least stable. It is the least electronegative. So acid number 3, all right, this should be HClO. All right, this one should be HIO, and this should be HBRO. And I believe the correct answer is then 2. All right, so now we're looking at this, talking about these are weak nitrogen bases listed. The nitrogen bases are A, B, C, and D. And then at the top, you can see too, all right, we got the bases listed at the very top line, and then below it are the conjugate acids. So we want to know, based on the Lewis structure of the conjugate acid, all right, based on the relative stability of the conjugate acid, which of the following has the largest value for Kb? Okay, so as Kb goes up, all right, we're more stable. Now, when it was an acid, we wanted, right? When you're an acid, you form a conjugate base. So you need to be high electronegativity. But we're not dealing with acids. It's opposite. It's a base. So bases that produce conjugate acids, they become positive. They need low electronegativity. They have to be happy. Can't use that word for real, right? But they gotta be happy being positive. Gotta be stable being positive, right? We want the one that's the least electronegative. So if we look at these 4 things, all right, we got our friends, they all have an N, but let's look who the N's attached to. We got a Cl, we got an O, and then we got another N, all right? These 3 things are highly electronegative, all right? These are highly electronegative elements, all right? That means these things are not happy being positive, right? These things are not. All right. Carbon is totally content being positive, right? It's fine. It can, it's no big deal. So of the 4, this one's the happiest being positive. This is the most stable. All right. This would have the highest Kb as a base. So methylamine is going to be your answer. All right. Very briefly about polyprotic acids. All right. There is really nothing much you ever have to do with this ever. All right. Except for really this part down here. All right. So we can figure out how many protons you had by figuring out how many equivalence points you have. There's no ever math with a polyprotic acid. So if I look at this, all right, I have an EQ point and an EQ point. So I donated 2 protons. So if you were given a list and said, hey, which of these acids, cyanidic acid, carbonic acid, nitrous acid, or phosphoric acid, could have been, was titrated this curve, which of these acids would be, representative of this curve? And it'd be this one because there are 2 protons. Have a great Friday, guys.